Hello, everyone. My name is Awadong, and today I'll be presenting a paper that was recently accepted at ICRA 2025, and it addresses the problem of fine-tuning pre-trained robotic behaviors using preference-based reinforcement learning. So here's the outline of the presentation. I know some of you have a background in reinforcement learning, so I'll just do a quick review on reinforcement learning and what is preference-based reinforcement learning, and then I'll present the paper's motivation and main results. At the end, I will share my thoughts more on a viewer's, reader's, or reviewer's perspective. So let's start with some context. So we all know that classic reinforcement learning excels at learning from interactions, but may struggle sometimes with user-specific preferences. The reason behind this is that it relies on a well-defined reward function, which may not translate well to new and seen contexts, especially after, for example, converging to a specific policy. Preference-based reinforcement learning solves this by learning the reward function itself through pairwise comparisons. So for example, we show a human two videos of a robot following a user, and we ask which one represents better following from the right side. So this is what we call a human preference. However, this method also comes with the expense of collecting human preferences, which is time-consuming and expensive. This is also where the paper's focus is, which is style adaptation. So the authors apply a reinforcement learning method to adapt robotic behaviors based on these human preferences and making sure that the robot still performs the original task. So for example, let's look at this example from the paper. Imagine you trained a robot to follow a user and to avoid collisions at all costs. And now you want the robot to actually follow the user from the right side. This is what we call style adaptation, or in other words, fine-tuning. However, fine-tuning for this new behavior can cause a problem called catastrophic reward forgetting, where the robot forgets its original capabilities, or in other words, we lose original information from the model after fine-tuning. So with this in mind, we actually have two problems, right? One, which is collecting human preferences is time-consuming and expensive in robot preference learning. And two, we want to adapt behaviors based on these user interactions and preferences, but we also don't want to lose the robot's learned capabilities before. So to tackle these challenges, the paper proposes a low-rank adaptation, or LoRa in short, of the reward model when fine-tuning behaviors to new preferences. The key contributions are: one, the paper first identifies catastrophic reward forgetting as an issue in low preference data regimens for robotic tasks. And two, it introduces LoRa to adapt the reward model more efficiently. And three, it shows that FLORA, which is LoRa applied to preference-based reinforcement learning, mitigates this issue of catastrophic reward forgetting while still achieving style adaptation. And in most cases, it uses less than 100 human preferences. So to understand CRF better, we can just look at this example of the task of closing a drawer. So this is the original rewards, and we can see that there's a clear separation between good and bad state action pairs defined by the color green and the color red. However, when we apply fine-tuning or surf when adapting to new human preferences, it destroys this structure, leading to catastrophic reward forgetting. Flora, on the other hand, adapts the reward model to human preferences while still preserving the original task performance. This is shown just by the broad region of high reward values in the state action pairs. So very simply, Flora works in two steps. The first step is pre-train the reward model on the original robotic task. And two, it fine-tunes using low-rank adaptation to adapt to new preferences. This approach basically reduces the number of trainable parameters in the neural network of the reward model and is actually supported by previous work in which it shows that pre-trained models have a very low intrinsic dimension. So in other words, there exists a low dimension representation that is as effective for fine-tuning as the full parameter space. And then, so the paper evaluates this method on simulation benchmarks and also in real-world tasks. Flora actually outperforms baselines like fine-tuning, surf, and co-training, and it maintains this original task performance, which we can see here by the color blue, and it still maintains a very strong style reward. In real-world tasks, Flora also performs really well. In the first task, which is following the user without colliding with them, and the adaptation being on the right side, we can see that it has a lower collision rate in comparison with surf and fine-tuning, and the distance is smaller, which is the adaptation. For the second task, we can also see that Flora pushes the drawer more and at a slower speed, which is also the adaptation part. So the conclusion is Flora is a novel and effective method for sample-efficient robotic-style adaptation, using in most cases less than 100 human preferences, and it addresses the issue of catastrophic reward forgetting in low data regimes and achieves strong performance in both simulation and real-world tasks. Okay, the presentation now is done. These are the references. And since I still have some time, I was thinking of just asking some questions that I have. I have them here. So overall, I really liked the paper. Specifically, I think it's really nice to actually show the problem first of catastrophic forgetting in style adaptation and show how fine-tuning leads to a loss of information, especially when data is scarce. And then just apply Flora, which addresses this problem, and it outperforms most original task performances while still adapting to style preferences. I also found it very interesting how the paper is built on well-known concepts, one which is training and fine-tuning neural networks, and the other which is LoRa, right? So low dimensional representation can actually be as effective in fine-tuning when data is scarce. Uh, the main takeaway that I have is I saw the appendix, and there's obviously a trade-off between optimizing task performance and also adapting to the style preference. And by design, Flora freezes the original weight. So I'm guessing that it helps mitigate CRF, but it also limits the extent of satisfying the style preference. And I think this can be seen on the table earlier, in which Surf or co-training actually performs always better than Flora in style adaptation. I think this makes sense for the scenarios shown in the paper, where task performance is more important, so like following user and avoiding collision and also closing a drawer. But I'm wondering how it performs for scenarios where maybe style adaptation is more important and doesn't have the same weight. So yeah, I would like to see that. That would be, I don't know if that's interesting. And another question that I have, which was mentioned briefly in the limitations, is how to systematically determine the rank of the matrix. So we know the rank depends a lot on task complexity, reward function architecture, and preference data set size, and even how the pre-training is done, at least from the paper of Laura. So I think it would be interesting to see how it adapts to other tasks and also to different model architectures. And lastly, uh, CRF or catastrophic forgetting is a well-known issue when we're fine-tuning neural networks. So I'm also wondering if there are other methods that try to mitigate catastrophic forgetting in preference-based reinforcement learning, and why wasn't it compared if it does exist? But yeah, thanks. I think that was it.